All right, how's it going, everybody? We are here for our second video of week 12. We're going to wrap up chapter 10 today by talking about our two other sample tests. We've already looked at all of our one sample tests a few weeks ago, and last video we looked at our first two sample tests. We already looked at our means of two samples, whether we're using a z or a t distribution in the previous video. There we were looking at means. Today we're going to see our two sample proportion test as well as our matched pairs test. Matched pairs are also going to be looking at means, but the difference will be is that we're going to be taking a sample from the same group of people two different times. So we're going to have a slightly different procedure associated with that one. In this case, we have two dependent samples. One sample is dependent on the other, and so we're going to do a slightly different process there. So kind of let's get started here. All we're really going to do is kind of follow the same structure of our previous video where we want to ask what's new and different about this scenario and then apply our same strategies as our one sample test to answer questions about comparisons between proportions and dependent samples here. So the questions that we asked in the previous video here about kind of updating our ideas are, what are the conditions required for this certain test to be valid? What are the things that have to be going on for our math to make sense here? How do we form our null and our alternative hypotheses? What do our hypotheses look associated with these new types of tests? And how do we compute our test statistic? We saw that's really the major change here is that we get a different computation to compute either a z or t score that's associated with our sample to determine how likely was that sample. All right, so we're still going to want to compute a test statistic, but our computation for that will change as it did in the previous videos. However, we'll still compute our p-values and form our conclusions exactly the same way as we've been in all of our tests so far. And notice real quick, when I say how do we compute our test statistic, notice that our test statistic always depends on us knowing this standard error term, the term that we're using in a sense in place of our standard deviation term. And so notice that's really sort of asking the question, what distribution does our difference in parameters follow? If we're comparing two proportions, we want to know the difference in sample proportions. What distribution does it follow? The standard error term will be sitting there to help us describe that and to help us compute our test statistics out there. So in a sense, all three of these questions are sort of getting at that same idea right here. These three questions, part of entry number 3 right here. So today we'll look at comparing two proportions, and then we'll look at matched pairs examples where the samples are not independent of one another. So let's go ahead and start with our two proportion scenario here. First of all, by the way, you'll notice there's some shorthand that's typically used for this, referring to this as a two prop z test. Two prop because there's two proportions that are being compared. A z-test because we're always going to be using the standard normal distribution to help us compute our probabilities associated with comparison of two proportions here. So a two-prop z-test is our shorthand for the comparison of two proportions using the z distribution. So the first question that we asked is, what are the conditions that are required for this particular test to be valid? Like under what circumstances can we go ahead and perform this two-prop z-test? Well, one thing that needs to be true is that we need to collect two samples. Those need to be simple random samples, and they need to be independent of one another. And so we saw some examples of this in the previous video. If you're sampling, and what we're going to see here is like proportion of men that vote versus proportion of women that vote, these are independent of each other because the men's responses are not going to depend on what the women's responses were. On the other hand, when we look at our later example, when we look at our matched pairs example today of, for example, weight loss, we're going to be collecting a before and after sample. And so therefore the after sample, the results of that sample will depend on what the before ones were. If all the people were heavily overweight in the before sample, they're probably all going to be pretty overweight in the after sample also. We know some information about the second sample in that scenario, but not in our proportion comparison here. These need to be independent samples that we've taken where the results of one have no influence on the results of the other. The other requirement here that's important is that we need to have at least 5 successes and 5 failures in the sample that was drawn. The reason why this is the case is because we end up getting really screwy results associated with our calculations if we're attempting to look at proportions of very rare events. And I discussed this when we talked about our one proportion sit-ups, and it's the same reasoning here. A good thing to think about is if you're trying to determine, for example, what proportion of citizens have brain cancer, only very few people have that, right? There's only going to be, less than 1 in 1,000 people that are going to tell you that they currently have or previously had brain cancer or something like that. So if you were to go and sample even 500 people, you shouldn't necessarily expect to find any that have had or currently have brain cancer. But that doesn't necessarily represent the fact that nobody has that disease or something like that, right? So in general, very, very rare events like brain cancer are a lot tougher to study because they are so rare in the population that it's difficult to take samples that will have some representative population of successes. In this case, we disappointingly statistically mean a success as having brain cancer, obviously not a success. But we need to see a decent number of successes and a decent number of failures um, for us to have a good sense of the sample being representative of the population. So it's true that these tests struggle with extreme scenarios such as having brain cancer because it's a very, very rare thing. So that means that the the science behind making estimates associated with that are a little bit more difficult to perform. We need to collect much, much, much larger samples to be able to perform reasonable math to make estimates about those sorts of things out there. So in general, this bullet point right here is sort of saying be wary of scenarios where it's extremely rare to have a success or to have a failure. If there's only one or two successes in your whole sample, that's probably going to your math might lead you astray in the beliefs that it will sort of crop up there. So we need to have at least 5 successes and 5 failures in any sample that we collect when we're talking about proportions. How do we form our null and alternative hypotheses? These ones are going to pretty much match up exactly with what we saw yesterday. Our null hypothesis is always our statement of no change or our statement of no difference. So therefore, it's still going to look like a null hypothesis saying something like the first proportion is the same as the second proportion. Notice that that is algebraically equivalent to saying the difference in the two proportions is 0. There is no difference. The difference is 0. That's what we've got in our 2 different statements right here. So either of these would be equally good ways to state a null hypothesis, our statement of no change or no difference. Our alternative hypotheses, as we saw yesterday, are going to include our greater thans and our less thans out there, as we've seen with all of our hypothesis tests so far. So our big question is, computationally, how are we going to compute our test statistic? So this one's going to give us a little bit of computation that we need to be careful with here. This isn't anything too crazy, but you got to be comfortable with your calculator to make some calculations happen here. So the first thing that we're going to do is we're going to define a new variable that's going to help us out with this calculation here. And so this is going to be referred to as our pooled proportion. So let me identify a couple parameters here. We're going to take 2 samples, right? These are all of our 2 sample tests, right? So we're going to have things like x1, our number of successes in sample 1, x2, our number of successes in sample 2. We're going to have our sample size for sample 1, our sample size for sample 2. We're going to have our proportion of successes from sample 1, and we're going to have our proportion of successes from sample 2. What we're going to do here is we're going to kind of combine some of this information into a single pooled proportion rather than having these be referencing 2 separate population or 2 separate samples out there. And we are going to compute a general p hat. Notice it doesn't have a subscript at all. This is the proportion of successes from sample 1. This is the proportion of successes from sample 2. This is going to be our overall proportion of successes, and this will be our total number of successes divided by our total sample size here. All right. So this is first our key for this guy is our step 1 is going to be to say compute the pooled proportion of successes across both samples that were taken. We will use this general p hat here, our general pooled sample proportion of successes, to help us compute our actual test statistic. All right, so this is sort of our step 1 for our test statistic, is we need to compute this sort of intermediary variable. Very disappointingly, it is another variable that's defined with the letter p. And again, you should notice here we are not placing a subscript on the p to indicate that this is coming in general from both of our samples items out there. Total number of successes divided by total sample size gives us our pooled proportion of successes. Then, in general, the difference of 2 sample proportions follows what distribution? So here's my difference of 2 sample proportions. That's a difference of 2 sample proportions is distributed according to the normal distribution. we're always suspicious, or excuse me, the null hypothesis is always going to tell us that the difference between these two should be zero, right? Our statement of no difference says there isn't a difference in proportions between the two groups out there. What we are very much interested in is the standard error term that we're going to use both in our confidence intervals and in our hypothesis test here. Our standard error term is going to use this p hat in its calculations here, and it's going to look like this guy. It's going to be a big old square root computation here. It's going to be p hat, our pooled proportion of successes, times 1 minus p hat. You should recognize that as like our q term. It's our sort of like our pooled proportion of failures right there, times 1 over our first sample size plus 1 over our second sample size. And as we kind of saw in our previous video, this does sort of look like a mash together of our of two different standard error terms from our one sample test. It's got a little bit of an issue that the sum of two square root terms does not equal the square root of the sum of two terms, but this hopefully does look vaguely familiar to you relative to what we had in our one sample test. In our one sample test, we had things like p hat times 1 minus p hat over n. In our one sample stuff here. And you can see here we have similar stuff like that. In fact, if you just ignore this 1 plus n over 2, then that's exactly what we have here. The only difference is that here p hat was just x over n. Here now p hat is, there's two different x's and two different n's, and it's taking them both into account right there. But this does look and feel to me similar to the one sample scenarios here. So again, the very important thing here is that the standard error term is this guy that's right here, and we will need to use this in all of our computations for both confidence intervals and significance tests that are associated with our two sample proportion tests here. So we can use this to compute z-scores for the hypothesis test. So maybe I'll just say here our z-score computation then is going to be, it's our p1 hat minus p2 hat minus p1 minus p2. And this, by the way, is equal to 0 according to the null hypothesis always. And it's all divided by our standard error term here. So this will be the way that we compute a z-score associated with our hypothesis test here. Yeah, so let's go ahead and look at some examples then, comparing two proportions. Example 1, a confidence interval. So our question here is, are women more likely to vote than men? Suppose we take a simple random sample of 200 Eurekans, and we find that of the 85 men that are polled, 42 voted, and of the 115 women polled, 70 voted. We'd like to build a 90% confidence interval for the true difference in proportion of men versus women voters. And we want to ask, is it possible that there's no difference in voting rates between men and women? Is that a potential result that we're going to be able to interpret from our confidence interval? So let's go ahead and, state the information that we know and that we want to know, and let's go ahead and compute our confidence interval that's going to be associated with this guy here. So first things first, let's go ahead and identify kind of all of the pieces of information that we're going to want to know here. And I'm going to kind of make a little table here. Let's see here. All right, so our sample size is here. We've got our N for men is going to be 85 men were polled. Our sample size for women is that 115 women were polled. Our number of successes for men was 42. Our number of successes for women was 70. Our proportion of successes for men is going to be 42 over 85. We'll get that calculation in a second. And our proportion of successes for women is 70 over 115 here. And let me go to my calculator here and compute some decimals for these guys. 42 divided by 85. I am seeing here a 0.4941. And proportion of women that voted, 70 divided by 115. And our sample was 60.87. 0.6087. All right. So we've got our proportions of success across each of the two groups here. And what we know is that we're also going to be interested in computing that pooled proportion of successes. That's going to be our p hat equal to x sub x for the men plus the x for the women divided by the n for the men plus the n for the women. Here it looks like we have a total of, I can just do this computation based on the numbers I've got right here. It looks like we're going to have here the, let's see, 42 men that voted plus the 70 women that voted out of the 200 total people that we have polled here. And we'll get a decimal value for this guy as well. And I'm seeing this as 0.56. So if we want to go ahead and compute a confidence interval now, we can use the information that we've accrued here for our confidence interval. We know that our confidence interval form is our point estimate plus or minus our margin of error As we've seen, our point estimate is always going to be the difference in the parameters that we're interested in. Our margin of error is always going to be of the form, let's see, let me just write one more line here, point estimate plus or minus. This is always going to be that z star or t star critical value times our standard error. All right. So our point estimate for the true difference in proportion of voters is going to be our sample difference in proportion of voters. So we're going to get here, and by the way, let me go back up and reread the question real quick. The question is asking, are women more likely to vote than men? That's indicating to me the order that I want to perform the subtraction that's associated with this comparison here. I'm thinking, this sort of seems to be suggesting to me that women are more likely to vote than men. So I'm going to form this point estimate as the proportion of women in our sample minus the proportion of men in our sample that voted, plus or minus, I'll just wrap this guy up in parentheses here. We're going to need to figure out our z star that's associated with this guy here. We wanted to form a 90% confidence interval. A 90% confidence interval is going to cover the middle 90% in the middle, 5% in each of the tails. So I know that where my z star value is going to live is where 95% of the area is to the left. So I'm going to go over to Excel real quick here. And in Excel, we can go ahead and ask ourselves, there's our coming up problem right there. And we'll see that in a second. I'm going to go ahead and ask, we want to do a norm.inv. My probability is 0.95, that's to the left. My mean is 0, standard deviation is 1. And that's going to be telling me 1.645 is my decimal that I'll use for z star there, 1.645. Let me come back over here. And now we need our standard error term. I'll just write standard error right there for 1 second. We'll go compute that once we fill in all of our values here. So let's do that. So we want to, let me grab some numbers here. So we want the proportion of women minus the proportion of men. So 6087 minus 0.4941. That's our point estimate. It does look like in the sample that we drew that approximately 11% more women than men voted, but that could have just been due to sampling error here. So we want to go ahead and compute our confidence interval to determine, was this due to a random chance or is this due to a true actual difference in the voters out there? So let's go ahead and form this confidence interval 6, 4, 5. And our standard error term is going to be our p hat times 1 minus p hat times 1 over n1 plus 1 over n2. So this denominator right here is exactly the term that I'm looking to grab as our standard error term here. We computed p hat to be exactly 0.56, so that makes things a little bit nicer here for our calculations. I've got a 0.56 times 1 minus 0.56 times 1 over each of the sample sizes here. My sample sizes were 85 and 115. So we have formed our structure of our confidence interval here. Now we just got to go to our calculator and do our little bits of computation here. So first things first, 0.6087 minus 0.4941. I'm getting a 0.1146. That's our point estimate. Our estimate is that in our sample, there was an 11.46% percentage point difference between the proportion of men that voted and women. That's how many more women voted as a percentage. I'm just going to leave my z right there, and let's go to the calculator for the stuff inside the square root. 0.56 times 1 minus 0.56 times 1, let's see, 1 over 85 plus 1 over 115. And I am getting 0.00504. And I'll go ahead and take the square root of that guy. And I'll multiply by the 1.645 that we'd seen for z. And what I'm landing at here is a margin of error of 0.1168 right here. So it looks like my confidence interval for the true difference in proportion of women versus men that vote is it seems like women are 11.46% more likely to vote, give or take 11.68%. So how do we interpret this? I kind of think I need to really go and do my addition subtraction here to see what we're getting. 11.46 minus that 0.1168 and the 0.1146 plus 0.1168. And if I go to my calculator and do these two, 0.1146 minus 0.1168, I'm seeing here a negative 0.002. Over here I'm seeing 0.1146 plus 0.1168, and I'm getting a 0.2314. So it looks like our lower bound for our confidence interval is a negative and our upper bound is a positive. So how do we interpret this guy here? So our question was, what is the true difference in proportion between number of women that vote and number of men that vote? And what we ended up finding here, and again, the order of our subtraction is actually important here. So let's say here, that was a 90% confidence interval. We are 90% confident that the true difference hold on, let me rephrase this. So, as I started telling you guys yesterday, it gets harder to phrase these two proportion ones, two sample test conclusions more so than the one sample one to phrase what we really mean here. And notice that the issue with this one in particular is that we got one positive number and one negative number. That negative number of 0.022 is going to tell me that the most extreme left bound here is suggesting actually that men might vote more than women, because this right here, this confidence interval is for the true proportion of how much more women vote than men. If women vote more than men by a negative number, then that really means that men vote more than women, right? But we can see that it's a very bare edge that we've fallen into the negatives. On the other hand, we're seeing in our 90% confidence interval for the upper bound that it's possible that women vote more than men by as much as about 23%. That's the upper bound. On the other hand, it seems that the most extreme lower bound case is that men actually vote more than women by about 0.22%. So we are 90% confident that the true difference in proportion between male and female voting rates is between 0.22% more men than women voters and 23.14% more women than men voters. Now, notice that there was one other question that we asked associated with this confidence interval here. We asked the question, can we rule out the possibility that there is no difference in voting rates? And what do we think here? So if there's no difference in voting rates, then that would tell me that the true difference is 0. And what I'm noticing is that the number 0 does live in this interval, because 0 is what's between negative stuff and positive stuff. Now, 0 is barely in this interval right here. If we were to have formed, for example, or if we were to take in a very slightly larger sample or had slightly less confidence associated with this interval here, then I would bet that the 0 would get budged out of there. But I'm going to say here, yes, it seems possible, since 0 is contained within our confidence interval, or the true difference in voting proportions between men and women. All right, so we can now kind of use this to answer questions about plausible values here, right? I'm seeing that since 0 is contained within our confidence interval, 0 is a possible value for us. Our best guess for the true value of the difference in the proportion is more like 11% more women than men vote, but it's completely possible, according to our 90% confidence interval, that 0 is actually the true difference in proportion of voters, because again, we only took a sample of 200 voters. That's not really representative of how many people voted in this election. It's something like 146 million people voted out there. We only took a sample of 200 people, so it's certainly possible that our point estimate here is not necessarily completely accurate, but that's fine. We know that every sample has some variation in it. We're never actually expecting that our point estimate, here our 11.46, is necessarily truly correct for the true difference in proportion. That's why we're forming the confidence interval, to say we're 90% sure that somewhere in this interval is the true proportion and difference of men and women voters. Now, as my final comment, I'll say this interval clearly favors women having a higher proportion of voting rates than men. It seems like there is a very small sliver of this interval that suggests that men are actually going to vote at a greater rate than women, but pretty tiny part of this interval right here. A vast majority of our intervals in the positive numbers, and since we set our subtraction up to be the proportion of women minus the proportion of men, any positive numbers are going to suggest that the proportion of women was larger than the proportion of men. So kind of notice here, the ordering of the subtraction really did matter for how we answered our question. If we would have done this subtraction here differently, then we would have gotten the negative of this result. We would have gotten a positive number here and a negative number here, and we would have inverted our interpretations here relative to the men and women. We still would have concluded the same thing, that it seems that women vote more than men, but if we phrased our question, how much more do men vote than women, and then took a sample that showed that women voted more than men, then we should find the difference in proportion to be negative, because how much more do men vote than women? By a negative amount, because women actually vote more than men. It's going to be how we might draw our conclusion there. So just kind of realize it's worth it to stop and think about in what order are you performing your subtraction when you're comparing two samples. It will influence how you kind of end up writing your conclusion and interpreting the confidence interval values that you got right there. So there's our first two sample for proportion confidence interval. Now let's go ahead and look at a hypothesis test associated with comparing two proportions here. In this example, we're going to look at a hypothesis test comparing two proportions. So recently, College of the Redwoods and many other schools have trialed what is the common name for this is something like supplemental academic instruction. At the previous school that I worked at before College of the Redwoods, we had the same program. It was referred to as the SAI program. And all that really happened here was lots of classes that typically have unfortunately high fail rates for the classes in which we want to sort of increase the number of students that pass the class is an additional 1 credit is included into the course to help students with maybe some prerequisites that they were missing beforehand. Things like that. Students that need extra help with the course, essentially taking a 4-credit version of a class that's typically only offered for 3 credits. So a very reasonable thing to be asking. This is something that every faculty and every administrator wants to know about the SAI program is, does it actually help students? Does the proportion of students that fail the class drop if they're in an SAI class? We should have fewer fails if the SAI program is truly helping students to achieve their goals, right? So what we, I think, sensibly want to do here is to compare a sample from SAI students to a sample of non-SAI students and see if the fail rates have some measurable difference between them that we can identify as being statistically significant with a hypothesis test here. So what we're going to do is we are going to sort of hypothetically choose some particular course. So it's not like we're comparing English and statistics students here. We're just going to say, let's pick a pool of just stat students, for example, and say, let's draw a sample of 96 of them that are getting supplemental academic instruction and 117 that are not getting supplemental academic instruction. Determine the number of students that failed so that we can compare the proportion of fails with the SAI versus with the non-SAI. And let's go ahead and determine at the alpha equal 0.1 level of significance if SAI courses improve student success. So let's go ahead and identify sort of the variables associated with this guy here, the numerical information we want to extract from these paragraphs, and then we'll start our hypothesis test with the same first step we always start with, our hypotheses. So let's identify our information here. So what do we got here? I'm going to call our So as far as labeling these things go, on our previous one we had men and women, so that was easy for us to label as M and W. Here, another thing I kind of want to suggest to you guys is that it's typically good to use numbers of 0 and 1 sometimes instead of 1 and 2, because 1 and 2 distinguishes just between two generic objects. But I typically think of 0 as sort of like a false or doesn't have it, and a 1 as a true or does have it. Or you can even think of like a power button, it's off or it's on. Here I'm saying that you do have the SAI class, that's 1. That's typically a true value, whereas non-SAI, that's 0. They didn't have it. So in my mind, 0 and 1 is a better like yes-no distinguisher than like 1 and 2, because 1 and 2 are both numbers that have value. 0 is sort of the non-valued number right there. It's the thing where you don't have any magnitude right there, a magnitude of 0. So I'm going to use 1s and 0s for my subscript, and 1 indicates the people that are receiving supplemental academic instruction. 0 means they did not receive supplemental academic instruction here. So I'm going to say here that we have an N1. Our samples, how many people did take SAI? 96 SAI students. And it says our 117 non-SAI students. 10 SAI students failed. Now notice here that we are going to be measuring fail rates. So in a sense here, this is our kind of a weird version that we are in a sense considering failing the class statistically to be considered a success. We're saying, did they fail or did they not fail? And so here, my number of failed students, that's my number of successes, is 10. And in the non-SAI group, we had 17 that failed. And so we can come up with our P1 hat and our P0 hat here, the successes of proportion of successes for each. So this should be our 10 out of 96, and this will be our 17 out of 117. We'll go hit our calculator for these guys. 10 out of 96 and 17 out of 117. And I am getting values here of 0.1042 and 0.1453. All right, so we've got our individual proportions here. As we've also seen, we're going to want to know our pooled proportion. P hat. That's going to be our total number of successes. That's 10 plus 17 divided by our total number of trials. That's 96 plus 117. And if I go to my calculator here, we've got 96 plus 117 is 213. So 27 divided by 213 is going to be 0.1268. So I think that these are all the numbers I'm going to need to perform the calculations necessary here. So now let's actually go ahead and set up our hypothesis test here. So our null hypothesis, always our statement of no change or of no difference. That's going to say to us that the proportion of students that are failing their class without SAI is the same as the proportion of students that are failing their class with SAI. What are we suspicious is going to happen for our alternative? What are we thinking we're going to show? Well, the whole point of the SAI program is to reduce fail rates, right? We want less proportion of fails. If we did take the SAI class is what we're suspicious is going to happen. So since P naught is our proportion of, remember, P naught is our proportion of fails without SAI. And P1 is our proportion of fails with SAI. So I'm thinking that what we're suspicious that we're going to show is that the students without SAI are going to have a greater fail rate than the proportion of students that do have the SAI class right here, right? Does that make sense? If P1 is our proportion of fails with SAI, we are suspicious that that will be smaller than the proportion of fails if you don't take an SAI class. We're trying to show, we're suspicious that taking this SAI class is going to reduce the fail rates for those students. So we're expecting a larger fail rate when you don't have the SAI class. That's what my hypotheses are saying right there. So for step 2, we need to compute a test statistic. We want to say, now that we've computed or performed the experiment, we want to compute the test statistic associated with the computation that we've done here. And so we've got our Z test statistic that we're going to compute. This is going to be our P1 hat minus P0 hat minus P1 minus P0, which the null hypothesis is always going to tell us is 0. All divided by that standard error term that we've seen before. So I'm just going to write that as standard error for right now. And then let's go ahead and throw some values into this thing here. So we've got our two sample proportions that we're seeing right here. I'm noticing a small thing right here. I think that I should be flipping this ordering based on how we're computing our test statistic. Notice that we're expecting this to be an upper tail test. And that helps me understand that we should be setting up our subtraction, should be that larger minus the smaller. So I think I really should be setting up here P0 minus P1. So I think I've got this backwards right there. So let's go ahead and we'll fix that once we actually write in our numbers here. For this P0 and P1 then, I've, let's see, 0.1042 and 0.1453. So 1453 so that's our difference in sample proportions. Our difference in the null hypothesized value of the difference in proportions, it's always zero. It's always our statement of no change or no difference. Our standard error term down here is going to be that p hat, 1 minus p hat, 1 over n1 plus 1 over n2. So what do we got here? We've got our p hat here, our pooled success proportion to be 0.1268. Times 1 over the first sample size. And our sample sizes were, let's see, 96 and 117. All right, so let's go hit our calculator for this guy and compute our z-score, our test statistic here. Our test statistic is a z-score in this case. We'll always do z stuff for our proportions. So up top, 0.1453 minus 0.1042. In our numerator, I'm getting 0.0411 divided by the square root of 0.1268 times 1 minus 0.1268 times 1 over 96 plus 1 over 117. And I'm getting, underneath the square root here, make sure you keep oh so many decimals for these tiny, tiny numbers in the square roots. You should be basically keeping everything that's in your calculator. And I'm going to get here, let's see, 0.0411 divided by the square root of that number I just got from my computation. And I'm getting 0.8969. So what this is saying to me is this. If the null hypothesis is true, and there is no difference at all between the true population proportions of these two groups, then that's going to tell me that the sample that we drew is less than 1 standard deviation away from that null hypothesized value of no difference right there. This is not a very unusual sample if the null hypothesis is true. That's likely going to lead us to say, we're going to go ahead and stick with the null hypothesis. If the null hypothesis is true, this sample is not a very strange sample relative to that null hypothesis. So this is not very good evidence that the null hypothesis is wrong, because our sample that we drew was less than 1 standard deviation away from average right here. So now that we've computed the z-score, our step 3 is always to compute our p-value. Our p-value is always the probability that if we were to perform this whole dang thing again, what's the probability that we'd see outcomes at least as extreme as the ones that we just saw? So here we're seeing our normal distribution. We've got our average at this at 0 right there, because we are hypothesizing with the null hypothesis that there is a 0 difference in the true proportions that are out there. And if there's 1 standard deviation, then we're really sitting right here, right? This is really our our z-score. Not talking our confidence intervals, it's not z-star. This is our z-score. .8968 or 69. And so our area of interest here is all this area out here. This whole dang thing is our p-value out here. Right? That's a lot of area. We're going to get a very large probability saying it's very likely that if we were to do this again, that we'd see more results that are like this. So to compute my p-value here, since it's an upper tail, I know that I want to do a 1 minus, because otherwise our norm.dist always gives us area to the left. I want an area to the right. So I'm going to do a norm.dist. I need to tell it our z-score of 0.8969 and my average of 0, standard deviation of 1, cumulative is true. And that is going to give me a p-value. We'll go hit this guy up in Excel. 0.8969 is my z-score. So coming back over to Excel, we've got equals 1 minus norm.dist. Our x value of interest is really our z value, 0.8969. Mean is 0, standard deviation is 1, our cumulative is true. And that's telling me 0.1849. All right. So this is a huge p-value right here, right? This is telling me, by the way, this is my z-score test statistic. This is my p-value. This p-value now is saying to me, if the null hypothesis were true, this p-value suggests that if we were to perform this whole experiment again, percent chance that we'd see results at least as extreme as we saw here. So all that's really saying to me here, and I'm doing some excessive rounding here, and you guys should stop rounding so much. But to say here about an 18.5%, that's almost a 20% chance, right? This is not a very rare event. This is an event that occurs almost 20% of the time if the null hypothesis were true, and therefore that's going to lead us to fail to reject our null hypothesis here. We don't have a bunch of evidence that says our null hypothesis is wrong. If the null hypothesis were right, events like this one would occur 18.5% of the time. It's a pretty common event then. That's not unusual at all. So for part 4, we compare and conclude. And I'll go ahead and type out our conclusion for this guy here. At the alpha equals, what was it, 0.1 level of significance, our data are not significant, meaning they did not show any statistically significant difference from the null hypothesis suggestion that there is no difference. Oh my gosh. Sorry, I forgot to switch over here again. I'm struggling to keep on keeping these straight. Let me restate what I said since I was never on screen for this. We computed a p-value of 0.1849, and what that is saying to me is that if we were to perform this whole experiment again, there's an 18.49% chance that we'd see results at least as extreme as this guy right here. That means that this was not a very rare event. It's an event that occurs 18.5% of the time. That's a thing that should happen then like all the time. It's almost a 1 in 5 occurrence right there. So this is not unusual relative to the assumption that the null hypothesis is true. And so therefore we don't have a bunch of evidence that claims that the null hypothesis is wrong. If the null hypothesis were right, events like this should be pretty common. And so this is saying we don't have sufficient evidence to reject the null hypothesis. We can see this numerically because our p-value here is greater than our alpha value. We want the p-value to be less than the alpha value if we are going to reject the null hypothesis. So at the alpha equal 0.1 level of significance that was provided to us, our data are not significant, meaning they do not provide any statistically significant evidence that the null hypothesis is wrong. Always good form to state your p-values so that people can know exactly how close the comparison perhaps was right there. We fail to reject the null hypothesis. And what was it that we were trying to kind of conclude here, right? Let's remember what this was all about. This was determining, does the SAI class help people fail less often? And the answer here is, it doesn't necessarily seem like it. We were hoping to show that the fail rates for the non-SAIs were larger than the fail rates for the SAI students, and we just didn't have enough evidence to show that. So we're going to stick with our null hypothesis here that says that it seems like these two are at least comparable to each other. So, and conclude that we do not have sufficient evidence to suggest that SAI students have lower fail rates than non-SAI students. And what I can also say to you, by the way, is that schools have seen wildly different rates of success with these types of SAI programs. Some schools have had a largely successful go with this, and a lot of schools have not. And so one of the things that we're seeing is that it doesn't seem to, in general, be the case that just offering an additional credit associated with the class and meeting for more time is necessarily increasing the pass rates associated with those classes. This is sort of suggesting to faculty and administrators that it's more about our prerequisite knowledge and our ability to be good students that is probably more the thing that's causing us to pass or fail classes, rather than just the number of hours of instruction received by an individual student in an individual semester there. And so again, it's not like there's no way to make these SAI programs successful, but lots of schools have sort of tried this and not really seen any large return associated with providing this extra time and effort and credit associated with these classes here. This is, while I did make up this data right here, this is not a unusual result for schools to have seen in this experiment that sort of happened out there lately. So there's our two difference in proportion examples. We want to look at one last scenario here, and the good news is that although this is a new scenario, this is going to boil down to being actually our simplest case in this week's content right here. So our last two sample scenario that we haven't discussed yet, remember there are 4 different 2 sample scenarios. Last video we looked at our 2 sample means for our z-test and our t-test if we have small samples or if we have large samples or normally distributed samples. Today we looked at our 2 sample proportion tests. Now we're going to look at our 4th case, our matched pairs test, when we have dependent samples rather than independent samples. We're going to do this one backwards. We want to kind of look at an example of this one before we try and answer our 3 update questions like we did for our proportion stuff here, to kind of feel out what's really going on. All right. So let's look at an example here to see, try and get some intuition for this guy. Suppose we wanted to determine if a proposed weight loss drug is effective. We're going to do this by weighing 8 people, then giving them the bottle of the weight loss pills, instructions for diet, exercise, and then we're going to weigh those same 8 people again 6 weeks later. And here are their weights. And I have listed this out as a before and after table. Very, very, very common setup for matched pairs is to look at before and after information here. So what are we interested in here? I mean, what we've been doing is taking 2 samples. We've been looking at 2 sample sizes. We've been getting sample averages, sample standard deviations, sample proportion of successes for each of the samples. But what's the thing that we actually want to know here? What's the variable that's actually interesting to you? Is it interesting to you to know that person number 2 weighed 261 pounds at the end of the trial? And here's maybe the way that I should really be asking this to you. What information can you tell me about the effectiveness of this drug by only knowing that person number 2 weighed 261 pounds at the end of the trial? And what I think the answer to that is, that tells me literally nothing. That person could have gone into the trial weighing 240 pounds or 280 pounds. I don't know if they lost 20 or gained 20 or stayed the same. Knowing just one of the samples' information seems to be useless to me. The other thing that I'm kind of seeing here is that it could be the case that most of the people in the trial lost weight, but maybe one person in the trial just abandoned this trial and just ate potato chips for 6 weeks and gained 30 pounds. I don't necessarily know that it makes sense for us to look at individually the averages and the standard deviations of the 2 samples. And my question that kind of helps me figure out what's actually the thing that's of interest to us here, what's actually our variable of interest in this problem, it helps to ask what would the null hypothesis be when determining if a weight loss drug works. If we were to think about a null hypothesis associated with this experiment, what would it be? Well, our null hypothesis is always our statement of no change or no difference. If this is a statement of no difference, then it would say to me that you did not lose any weight when you took this weight loss pill. That's saying to me the difference in before weight and after weight should be 0. And notice that what that's suggesting to us is that the thing that's actually of interest to us here is not the before sample, it's not the after sample, but it's the difference in weights between the before sample and the after sample here, right? What we are not interested in is anybody's before weight. We are not really interested in anybody's after weight because these are dependent on one another. What we are really interested in is what is their difference in weight, right? So what we're going to typically do in every one of our matched pairs examples is compute, instead of the two variables that are given to us, the before variable and the after variable, we're going to use those two to compute a third variable, the difference variable. Do the subtraction individually here. What I can see for this first person is that before they weighed 212, after they weighed 204, so it looks like their difference was -8. They lost 8 pounds over this trial. That's what happened to that one person. This person lost 2 pounds. This person gained 1 pound. This person lost 6. This person did a great job. This person lost 18 pounds. This person also did a very good job. They lost 15 pounds. This person only lost 2 pounds. This person lost 6 pounds. This is really my variable of interest right here. What was the difference? I want to know, is the difference 0? So what's going to be really nice about the matched pairs scenario is you're always going to be given 2 samples. But what your step 1 is always going to be is do the individual subtractions for each of the pairs in the samples and reduce yourself down to just a 1 sample testing scenario. So we now have 1 sample of a difference, and we can perform a 1 sample t-test on this difference that we're seeing right here, rather than dealing with all of the statistics associated with the 2 samples separately. Our variable of interest is the difference in the 2 samples. How much change has occurred, and is that change equal to 0 or not? Or is there a statistically significant difference from 0 for this change overall? So the great news for us is that despite the fact that this is officially a 2 sample scenario, because 2 samples need to be collected to perform this experiment, the computation that we're going to do on our end is a 1 sample computation, because we're going to combine the information from the 2 samples to produce the more relevant 1 sample, that is the difference between the 2 samples, and then perform 1 sample calculations on this difference sample that we have right here. So in general, a matched pairs scenario will always create a new variable, a third variable, to be the difference. And when I say difference, I mean perform the subtraction between the 2 samples, and we will then perform a 1 sample test on this new variable that we've created. So this one's nice and easy. You don't even get any new calculations. We're literally just going to use our t-sample test from 2 weeks ago, and that's all the new calculation that we need here. It's not a new calculation at all. It's stuff you've already seen. And maybe I'll remind you here, our t-sample test here is our t equals our x bar minus mu over s over root n. But, come on, pen, you can make it through this. Now, notice that I'm calling our mu not just mu, but mu sub diff. That's because our variable now is not the before weight, it's not the after weight, it's the difference in weights. So the mu here, mu is the true average difference in weights between the before and the after. We are always going to assume that our null hypothesis is always going to be there is no difference. The difference is 0. So this is really just going to boil down to x bar over s over root n, and that's all we're ever going to get right there. So that's going to be pretty easy. This is going to be our simplest calculations for us, aside from the fact that we need to produce our own column of data here. So let's go back and answer these 3 questions. What's changed here? What are the conditions required for this test to be valid? We need to draw 2 samples from the same individuals or same objects so that we can make a direct comparison, a before-after comparison. Either the samples must be drawn from known normal distribution populations, or the sample sizes must be large enough that the central limit theorem will say, hey, your sampling distribution will be normal even though the underlying ones weren't. So this is just our same rule as what we saw previously in our 1 sample t-tests. If the sample size is less than 30, then it needs to come from a normally distributed population. On the other hand, if our sample size is at least as big as 30, then we don't care what the underlying distribution is. The sampling distribution of the sample means will be normal even if the underlying one wasn't. And it's very typical in our match pairs examples to see these small sample scenarios here. That's what we'll see for our example. How do we form our null and alternative hypothesis? It's the same as really now the combination of our 2 sample and 1 sample tests, right? Saying that our before and after difference is 0, right? That's what I've got highlighted right here. the average value of the afters minus the average value of the befores is 0, or we just say that the average difference is equal to 0 right here. This is more appropriate for our one sample computations. This, in a sense, maybe our slightly more appropriate way to categorize this one here. Finally, how do we compute our test statistics? Same as we've done with our t-tests of one sample, and that's the thing I already wrote for you right there, which is the t equals the x bar minus mu over s over root n. And it should always be that our null hypothesis will say that mu is 0. Our true average difference is 0. That would say the weight loss pill doesn't do anything. There's no difference, right? It's always going to be our null hypothesis there. So let's do an example here and call it a day. So the one exciting thing that's going to go on in our example right here is that it's not going to be the test statistic because we've already done stuff that looks like this. The exciting part of this example here is going to be that you're going to be given tables of data for this, and you need to create your own column of data for the difference and compute your own average and standard deviation. I'm going to show you two convenient ways to do that here today, one in Excel, one in Desmos. So let's look at our final example for the day. The GRE, when you think of the GRE, you should think of this as the same thing as the SAT or ACT, except SAT and ACT is to get into an undergraduate college. The GRE is just to get into graduate school. So it's sort of just the next step up there. GRE is a standardized test used for graduate school admissions. We'd like to determine if taking GRE prep courses results in better performance on the GRE. And so this is a thing where you can imagine lots of people really care about getting into great graduate programs. So you really want to score well on the GRE so you can get into that good school, which means that lots of people are willing to pay lots of money to take these fancy GRE prep courses out there to try and improve their scores. And what I'm going to tell you going in, I shouldn't ruin this and give you any bias up front, but pro tip, these basically don't work. And I'll tell you more about this at the end out here as to why this is sort of a well-designed test in that sense. Let's go ahead and do the math here and see what we're going to see. We take a sample of 13 people's scores on their first attempt at the GRE. Then those 13 people are going to take a GRE prep course. And then they're going to take the GRE a second time, and their scores are going to be recorded a second time. Let's use the scores provided below to determine, at the alpha equal 0.05 level of significance, if GRE prep courses help improve people's scores on the GRE. All right? So we've got persons 1 through 13. They've got their before scores. They've got their after scores. By the way, GRE is really strangely scored. It's like between like a 120 and a 180 or something like that is the scoring possibility. So like a 150 is average. These are normally distributed scores out there, an average of 150. And your total possible best score then is like a 360 or something like that. It's a slightly weird scoring system out there, but all these scores are just kind of whatever. There's weird reasons why they designed the scoring systems to be the way that they are. So in any event, we've got our before and our after scores here. And what we know is that what we are really interested in is producing a third column here, a difference column, and then performing a one sample test on the statistics associated with the one sample or the single difference column that we're going to produce here. So the real question is, what's the easiest way for you to get a difference column? Because I don't want to sit here with my calculator and do 13 differences, and even worse if it was like 30 differences out there, and then there's decimals, and I don't know. I want a computer to do this for me is basically what I'm saying. So there's 3 ways that you can do this. One, the way that I'm not going to do right now, since I don't have a way to display my calculator to you, is that in your TI calculator, you can enter these before and after items as a list in your calculator, list 1 and list 2. You can then create list 3 to be the difference, list 2 minus list 1. It's not too crazy of a thing to do. If you're savvy with your TI calculator, I'm sure you can figure it out pretty easy or with some quick Googling how to make lists and then make a new list based on old lists. Not really too hard at all. I just can't display my calculator to you, so I'm not going to show you that right now. What I am going to show you is an easy way for us to get this either in Excel or in Desmos. I'll show you some nice things for each of these guys here. So really our issue here is we need the statistics. So I'm going to say this right now. Oh, unless I've lost my stylus. Okay, am I not? We need X bar and S for our sample of differences, right? I know that where I'm going with this is that I need to compute a test statistic to perform my hypothesis test. And so I'm going to need to compute a sample average, and a sample standard deviation for the difference in test score between the before and the after. So I need to get a third column, and I need to compute the average of that third column, and I need to compute the standard deviation of that third column. So I feel like I don't want to get too out of order right here. I'm at least going to do my hypotheses first, then we'll do our calculations in the order that we should be. So I'm going to say first my hypotheses. And here, our null hypothesis is that the average difference is 0. On the other hand, I'm thinking that our difference should be positive. We should have a positive change in score if the GRE prep course worked. So that's my null and alternative hypotheses, that the change was 0 or that there was a positive change. People improved from one step to the next. So for step 2 now, we need to compute a test statistic. So we're going to compute a t-test statistic. I'm noticing that we only have 13 observations here. So let me move this down to the end. Right. So I know that I'm going to compute t equals x bar minus mu over s over root n. We know mu is 0 according to the null hypothesis. We're always assuming the null hypothesis is true, letting that take us to a crazy place if it's wrong. We also know that n is 13. Need x bar and s from diff column. So let's go create the diff column and get Excel and Desmos to both give us the information that we want. So here's what I'm going to do, because our next step is to compute this, but I don't have the statistics yet available. I need to compute my difference column, and then I need to get my average and standard deviation of the difference column. So check out how this is going to work here. This is pretty dang nice. I'm going to do this first in Desmos, which we haven't seen before, and then we'll verify that the Desmos things match the Excel stuff that we have seen before. So I'm going to copy this. I'm going to Control C right now to copy that guy, and I'm going to come over into Desmos over here. And oh man, I've already got it in here. That's okay. I'm going to show you guys that we can just start with a blank screen on Desmos. So I did Control C to copy that chunk of the table. I'm now just going to Control V into this first blank spot in Desmos. And awesomely, check out the fact that it just plops this whole thing in here as a table. That's really convenient for us because now we can do some table manipulations here. All right, so these are all the values that we saw before. And by the way, the graph is going to do like nothing for us. I'm going to use Desmos as like a calculator here. What I want is a third column that's the difference of the two columns. And so if you can see here in my video, you can vaguely see some light lines right here suggesting that it's possible that this table could continue on. I'm going to click in this empty third column right here, and notice it's giving me a text box that I can write in. What do I want to be in this box right here? Well, I want this to be their final scores minus their initial scores, so I can see what change they experienced over time. It looks like Desmos auto-interpreted my initial scores as X1 and my final scores as Y1. We can change those labels. I'm just going to leave them alone right now. Again, X1 is my before, Y1 is my after. So I want my new column to be my after stuff minus my initial stuff right there. I could just literally type y1 minus x1, and it just did all the subtractions for us in this column, right? So thing one that's really cool is that Desmos can do some of these column manipulations that we might want to do. Now the thing that's actually even better, this is something I've sort of recently realized must be true about Desmos, is that it can do some good statistical calculations for us as well. So we now know that y1 minus x1 is actually like our variable of interest. It's our difference in the values over the before and the after. What I need to know is what's the mean of this difference. So I can ask, what is the mean of the y1 minus x1 column? And it's going to show me that the average change in score is an increase by about 1.5 points, about. It's a positive number, so I know it's an increase, and I just rounded more than you should ever round, so don't round that much, but about 1.5 is our increase right there. The other thing we need is our standard deviation, and STDDEV will do that for us, y1 minus x1. And that's going to tell us our sample standard deviation. So this is our x bar of interest in this problem. This is our s of interest in this problem right here. So I'm seeing a 1.46 and a 4.07. Let's go do this exact same thing in Excel so that you can see that these numbers match up, that you can trust both sources here. So pretty handy stuff right here, right? I copied and pasted into a blank cell and it filled in the x1, y1 in the columns. I was able to add my own column by doing math using the other column names that were over here. And then I did my mean and my standard deviation using that same thing, y1 minus x1, y1 minus x1. That was what that actual column itself was right there. And that gave me the mean and standard deviations of those columns. So that's real quick and easy. Everybody has access to Desmos. Alternatively, we could have done the same stuff over here in Excel. So let's go ahead and do that here. I'm going to get rid of my two computations from earlier. I've still got this thing already copied, so I'm ready already to Control V this thing. I'm just going to click on the upper left corner that I want, and I'm going to hit Control V. And very nicely, it plops in the whole table as I'd already seen it from Microsoft Word into Excel here. So let me zoom out a little bit so we can see some stuff. So this I know was my before column. This was my after column. So this should be my diff column. I always want to do my final minus my initial when we're calculating a difference. Always the later minus the earlier to get our correct ordering for the difference here. So what I'm going to do in Excel in this upper cell right here is I'm going to say equals. Always equals first when you're doing a computation. I want my after value. That looks like C2 minus my earlier value. That looks like B2. So I'm doing C2 minus B2 here to get my after minus before. And that tells me appropriately that that person increased their score by 2 points. Now, and I know it's slightly tough to see right here, what you can see here is there's a little square in the lower right-hand corner of this cell. I'm not clicking on the cell in general. You've got to click, so notice that I've got this like empty cross right here that's got white in the middle, and then it turns into more of a thick plus sign right there, a bold plus sign. That's what I want. That bold plus sign tells me I'm on the box right here. I can now, oh wait, sorry. I got to start on the cell that I've already done my math in, C2 minus B2, and I can now click and drag and it will perform the representative equivalence computation for the following rows here. So if I can click and drag like that, then it's going to do that same difference in computation here. It's always good to stop and do a quick spot check, like does that 10 make sense? And I look over and I see, yeah, that person clearly did increase their score by 10 points. So it seems like that click and drag did it for me. So I can see now that the values D2 through D14 are what's currently now holding my difference values right here. So I'm going to go ahead and compute a mean and a standard deviation associated with these guys. So I'm just giving those as word labels for myself, mean and standard deviation. Since I'm doing a calculation, I'm going to do equals. Equals. In Excel, it's called average, which honestly kind of surprises me that it's not mean. We saw that D2 through D14 were the values of interest. And by the way, you can stop and scroll up and see if it snagged the right ones. All that stuff in blue is what I want the average of. And I'm going to hit enter. There's that same 1.46 that you saw in Desmos. I can also go ahead and do here equals standard deviation. And I am remembering I want the standard deviation of the sample. So I got to do dot S. And again, I'm going to do D2 through D12, or D14, sorry. D2 through D14. And that's going to tell me that same 4.07 that we saw in Desmos as well right there. So it looks like these are in total agreement with what we saw in Desmos. So just realize that Desmos actually works. I always just think of Desmos as a graphing tool, but it's actually pretty useful as a quick calculator as well, even for statistical type things. And even, by the way, check out this other thing that I wish I kind of would have noticed earlier this semester. Wait, I'm back over in Desmos real quick, and this is just to show you a thing I didn't really realize that Desmos could do. Histogram is actually a command. And I could even have it make for me a histogram of the y1 minus x1 values. And this is showing me my histogram of those differences that we see right there. Right? So Desmos actually does some extra cool stat stuff that I maybe should have used a little bit more directly earlier this semester, but realized that, and look, it even gives you like the options. We can get our relative frequencies instead of our exact frequencies. We can center the bins centered on a value or left with the value. You can change what your bin width is and all that kind of stuff right there. A bin width of 2 maybe, stuff like that. So Desmos has some pretty good stat stuff in it. I didn't really even realize that, and it's maybe something that we want to take advantage of more in the future. So in any event, I've got the two computed values that I want. I've got x bar, I've got s, and so let's go back to Word and perform the remainder of our calculations here. So I'm back in Word, and let's now go hit up the rest of this calculation. We just saw that we were getting x bar and s. X bar was 1.462. S was 4.075. So now we can go ahead and compute our test statistic. That'll easily get us a p-value, get us our conclusion, and we will be good to go. 0.462 minus our null hypothesized difference of 0 over 4.075 divided by the square root of our sample size. We sampled 13 people. I'm going to go hit my calculator with this computation right here. 4.075 divided by the square root of 13. And then I'm going to do 1.462 divided by that answer. And I'm getting here 1.294. That says to me there's a little bit more, about a 1.25 standard deviations above normal for this result, if it were the case that there is no true difference really in taking a GRE prep test or not. Right? So now we've computed our test statistic. For step 3, we want to compute our p-value. And so for this guy right here, we know for the t-distribution, we need our degrees of freedom. We're very lucky that we're not performing a 2-sample t-test right here because we'd need our gross formula. Instead, because this is a 1-sample test, it's just n minus 1. So in that case, for us will be 12. Since we had 13 observations in our sample, we'll have 12 degrees of freedom. We were suspicious that this was going to improve our scores, so this was an upper-tailed test. We thought that the true average difference was going to be 0 according to our null hypothesis. And we saw that there is a t-value of 1.294 right here. So our p-value is all this area out to the right. So to compute this p-value, let's go hit this guy up in Excel. It's an upper tail, so I know I got to do 1 minus since Excel always computes left tails all the time. We're going to do a t.dist. It's going to want that t value, the 1.294. It's going to want our number of degrees of freedom, that's 12. And I think it wants true for that cumulative in there, right? I think that this is our appropriate t-distribution inputs there. So let's pop on over to Excel and throw that guy in here. We should be seeing, right, I'm doing my Excel computation here, equals 1 minus t.dist. My t value is the 1.294. My degrees of freedom was 12. Cumulative is true. And this is telling me 0.11001. So I'm pretty good with calling that just a 0.11 right there. I'm going to keep an extra 0 on the end because that helps me know that I'm not just rounding away to nothing. That's helping me know that that is accurate to 4 decimal places right there. So this is, oops, that's not t, that's our p-value right here. So what this is saying to us is that if it's true that there is no difference whatsoever in taking one or not, that this sample would be something that happens like 11% of the time, which again is pretty common right here. So notice again that our alpha value was zero point 0.1, our p-value was 0.11, and therefore our p-value is greater than our alpha value. This does not exceed our threshold of weirdness for ourselves. So let's go ahead and compare and conclude. Let me get my cursor down here. And we can say at the alpha equals 0.1 level of significance. Again, it doesn't seem like our p-value crossed that threshold. It's larger than that. This event was not quite as rare as our rareness cutoff. We needed to see an event that only occurred as rarely as 10% of the time or less. We saw something that occurs 11% of the time. The alpha equal 0.0 or 0.1 level of significance. Our data are not significant. They do not represent a significant departure from the null hypothesis suggestion. So I'm going to say our p-value equals 0.1100. Therefore, we fail to reject the null hypothesis and conclude that there is not sufficient evidence to suggest that taking GRE prep, Let's kind of back off on my statement right here. So the reason I'm kind of being careful with my conclusion here is because we don't want to kind of overstate what we know and what we don't know here. Really, my issue here is that the point here is we can't necessarily claim that there's a cause. Even if we did see a very small p-value and determined that there was a difference between people that had taken the prep course versus those that had not, there's lots of other confounding variables here. Oh my gosh, I'm sorry. I'm going to just keep on messing this up at the end right here. We're trying to make our comparison and our conclusion right here. Our alpha value is 0.1. Our p-value is 0.11. Since our p-value is larger than our alpha value, that says this was not as extreme as we wanted to see to reject the null hypothesis. To reject the null, we were going to need to see an alpha p-value that was less than 0.1. We saw the one that was more than 0.1. So therefore, we're going to fail to reject the null hypothesis and conclude, and I'm kind of saying here what? Here, all we can really say is that the students who took the GRE a second time after taking it once, then taking a prep course, didn't do statistically significantly better than those that just took it once. What we can't state here is some cause and effect relationship necessarily because we did not apply an experimental treatment to each of the individual groups here. We just took a group of people and they all took the GRE the 2 times with the prep course in between. You should certainly realize that there's lots of things like anxiety that are associated with standardized tests. If we did see that there was a big improvement in test scores, it's not necessarily because of the prep course. It might just be because people are more comfortable taking the test at that point. So remember to not kind of overstate our conclusions when we're looking at drawing these conclusions associated with this stuff here. We certainly don't necessarily have cause and effect relationships if we are not applying experimental treatments to groups rather than just making observations, which is what we did in this case here. This is certainly an observational study rather than an experiment with treatments, and so we want to be a little bit more careful about those conclusions that we're going to make. And at the end of the day, so now I'm done talking about stats, and I'm just going to tell you briefly about the GRE. If you're one of those people that's going to need to take the GRE later in your life, the thing that you should know is the GRE is very hard because the verbal section of the GRE has a lot of vocab on it. It's just a vocabulary section, and it's been shown that there's just no good way to study for that. There's just thousands and thousands of words. The likelihood that you're going to study a vocabulary definition of a word and then actually see it on the GRE is close to none. And so there's lots of people that pay thousands of dollars for GRE prep courses that showed no difference in scores before and after. And that kind of makes sense. And what I've heard from lots of very smart people, the advice that I was given for taking the GRE is if you want to do good on the GRE, go read a freaking book. Your vocab needs to be good. You need to be able to talk good and read good and know your Latin roots of words and stuff like that. So literally, like if you're planning on going to grad school, you're going to need to take the GRE, and there isn't really a good way to study for the GRE. The math there is, the verbal section there's not. So be well read. I think that I crushed the GRE because at least I used to read tons of books all the time. I have a very broad vocabulary just because I read a lot. It had nothing to do with studying, and I crushed the GRE, and I know that that's kind of wise because I'm well read. So read a lot of books. That's a good thing to do to make sure that you're a worldly person in general. I really like the fact that the GRE is not a test that you can study for, and that it's really just a sort of a measurement of are you comfortable with, like, can you recognize words that you maybe have never seen or haven't seen in a long time kind of thing, as far as the verbal part of this goes. I enjoy that as part of the challenge. So if you're going to grad school, find time to just read books. They don't need to be academic. You should just read a lot. So that wraps it up for me today for all of our two sample things. We looked at two sample proportion tests and confidence intervals today. We also looked at matched pairs example, where we really just reduced the problem down back to a one sample test that we'd seen weeks before. So hopefully both of those two things did not blow your mind here today. Next week, we're going to pick up with a brand new test that's going to look different than everything that we've seen before. It's still going to be a significance test, a hypothesis test. It's still going to follow our same four steps of hypothesis, test statistic, p-value, conclude, compare, and conclude. But we're going to have different structure and different setup for these. Next week, what we're going to look at is testing for goodness of fit. That means we're going to test to see if a distribution of results matches a proposed distribution or not. So far, what we've done is we've asked, does the sample average match a proposed population average? Does a sample proportion match a proposed population proportion? Next week, we're going to ask, does a sample distribution of results match a proposed distribution of results? And so that's sort of a different question out there. Instead of saying, where are our results centered? We're asking the question, how are our results shaped? And that's a different type of question than what we've been asking so far. In my opinion, this chi-squared test I think is like probably the most interesting part of this whole class. So I'm very much looking forward to chapter 11 content next week. I really like the chi-squared stuff. There's so many really interesting questions that we can ask and answer with that information there. So we'll see that stuff next week. Chapter 11 is what we're hitting next week. The chi-squared test for goodness of fit. So I will see you guys for those videos next week. Have a good one.